Right. Thank you for the introduction. Hi, everyone. My name is Mohammed Umair, and today I'm going to be talking about my topic, which is towards naturalistic turn taking in spoken dialogue systems. And I just want to start off by saying I appreciate you all being here. Um, so, what is turn taking in human interaction? And what is the importance of turn taking in human interaction? When we're all having a conversation, we are able to rapidly switch between who is speaking. And we know from a lot of research in human interaction that smooth turn taking is very important in how we interact and ensures that we can actually understand each other. And there's a few cool properties of smooth turn taking. The first is that turn taking is very rapid. So we're speaking at like 200 milliseconds on average, which is much faster than our response time for other stimuli. Speaker allocation occurs on a turn by turn basis. So we don't actually know who's going to speak before we actually, start our turn. And then we use deviations from our expectations of how turn taking is going to go to convey additional social information. So for example, we might delay our response to communicate hesitation and so on. So now I want to play an example of turn taking in human interaction. Hopefully the audio will come through.
It also makes me want to have hot chocolate and sit in front of a fireplace.
There's no fires that are really physical off.
There's too many fires in California.
No, like fireplaces.
Oh yeah, I haven't seen a single one.
So the thing to note there is that the switch between the speakers was very rapid and very smooth. And it seemed like almost they weren't putting any effort into doing that. But we know that's actually a very complex process. Now I want to first define what spoken dialogue systems are. So in my definition, spoken dialogue systems are just generally systems that can process speech and produce spontaneous dialogue. And we know that developing naturalistic open domain dialogue systems is important. And what we mean by open domain here is that they're not like oriented towards a specific task. And I do want to say that there's many different types of spoken dialogue system architectures, but that's not what we're focusing on right now. Usually we want to optimize these spoken dialogue systems on some metrics, right? So we want these systems to be very engaging with the users. So we want people to actually come back and talk to these systems. We want the system responses to be very coherent, but we also want the way in which those responses are delivered to be very coherent. And then we want the communication itself to be very efficient. So we don't want to have miscommunications with the system that might prevent us from having a smooth conversation. So why do I care about naturalistic turn taking in spoken dialogue systems? Again, we know that most of these spoken dialogue systems, they fail to replicate naturalistic turn timing as humans do, as in the example that we just saw. In the example that we just saw. And then this adversely affects the experience of the user in several ways. The first is that the system might be interrupting the user as they're speaking, which by providing untimely feedback, which can cause some sort of miscommunication. Since the system isn't really aware of the norms that are surrounding turn timing, it can't actually exploit these norms to convey additional information. So it can't like delay its turn to communicate hesitation and so on. And then we also know that humans actually identify a spoken dialogue system as the source of this trouble in conversation, and then they react in certain ways. So they might be amused or frustrated. So we do know that humans identify spoken dialogue systems as the source of this. So here's an example of ChatGPT, which is like a new spoken dialogue system. The important thing to note here is not the content, but actually the time between the turns that it takes for the system to respond.
We want to hear a bedtime story. Tell us a story about the super duper sunflower hedgehog named Larry. Start with telling us a little bit about him. Larry was a unique hedgehog unlike any other. He had bright sunflower petals instead of spines. Residing in Meadowville, Larry spread joy and color wherever he rolled. People cherished his radiant presence.
So it was very obvious compared to the human conversations that we just saw that the system took a very long time to respond compared to the humans, and the turn exchange wasn't smooth. So the goal of my research is to improve naturalistic turn timing in spoken dialogue systems. And I want to do this by developing models that are grounded in an understanding of human interaction. And there's going to be a number of benefits to having this type of communication and dialogue systems. The first is obviously that there's going to be reduced miscommunication between the user and the system because the system's not going to interrupt the user. Since the system will meet the user's expectations of the turn-taking system, there's going to be a reduced cognitive load on the user. And then if we ever want to have dialogue systems that can efficiently interact in multi-party settings, so more than two speakers, then we actually need their timing of their responses to be very accurate. So today I'll go over three different approaches that I took and three different problems that I tried to solve that kind of build towards this goal of having naturalistic turn timing in spoken dialogue systems. So the first is analyzing human conversations. We know that when we as humans are communicating, we use specific features to be able to achieve smooth turn timing. And the first question is, can we identify these features at scale? And our approach was to develop an automated transcription system to be able to identify these paralinguistic features of conversation. So what do I mean by paralinguistic features of conversation? They include features such as speech rate, overlaps, silences, and laughter. And they are non-lexical aspects of speech that carry strong interactive meaning. So they communicate a lot of information to us that's not just within the words and the timing of the words. And so we use these paralinguistic features to infer meaning, and we also use these to predict when we can actually speak in the future. So let's take a look at the transcript that I showed earlier of the two people speaking. This is just part of that. And we can see that the transcription that was generated by a commercially available speech-to-text system contains the turns, the words, and the timing of the words. But there's a lot of information that it fails to capture. So for example, it doesn't capture overlaps between the two different speakers if they occur. It also doesn't capture stretch speech markers, which are also very important. So for example, if I said what compared to what, the meaning is very different. It also doesn't capture pauses and gaps, which we know can communicate things like hesitation or frustration. So what we currently do not have are transcripts that annotate paralinguistic features of conversation, and we don't have the ability to do this at scale. And there's a number of roadblocks that prevent us from doing this. The first is that manual transcription in this specialized format is really difficult to do, and it requires experts and a lot of time. The general rule is that 1 hour of audio to transcribe in this format takes 15 to 20 hours to do by hand. So that's, we can't generate data that way. And then each individual feature is really difficult to identify. So like prosody or laughter or relative speech rate of the speaker can be like subjective decisions. And then we also know that speech-to-text systems are fundamentally limited in their accuracy as well. So if we're doing any downstream analysis, that's limited by the accuracy of the speech-to-text system itself. So how did we solve this problem? We invented a tool called Gilbot, which is used to generate transcripts containing paralinguistic features of conversation. Gilbot just won the SAGE concept grant this year, and we've published it. And it generates first draft transcripts that can be incrementally improved over time, and it contains annotations of a majority of these features. How does Gilbot work? So the first thing that Gilbot does when you give it some sort of audio file or video file, it uses multiple speech-to-text services to first get the word orthography and the timing as well. So it can use speech-to-text services like IBM's Watson, Google's Cloud's speech-to-text service, and then OpenAI's Whisper and WhisperX. And some of these models run on the cloud, some of these can run on your local computer, but we get the word and the timing of the words. The next step in Gilbot is analysis. So this is where Gilbot kind of shines. Gilbot has this framework where people can develop such plugin suites, which are represented by this kind of directed acyclic graph here. Each node in this graph is a plugin that detects one feature of conversation that users can define. And then once there are no dependencies for a plugin to run, it executes. So for example, in this case, the turn construction plugin would run first, and then the laughter and diarization plugins would run in parallel, and then so on. And this architecture allows us to parallelize a lot of the computation that we're doing. It also allows users to develop multiple of these plugin suites and run them all at once using Gilbot. So the output of Gilbot is text encoding initiative compatible, which means that we can use the Gilbot output with existing tools that we have, like CLAN and ELAN, for further analysis. Another benefit of doing this is, let's say I ran an analysis using a particular plugin suite, and then I developed a new plugin suite and I wanted to run a whole corpus again. In that case, I don't actually have to retranscribe everything. I can directly run the analysis, and that makes the whole process very efficient. So here's an example of a transcript that was produced by Gilbot. And we can see that it has certain features here. It has the thread speech markers, it has overlaps, and it has silences. So with that, I want to turn to the second part of my research. So we know that humans use paralinguistic features to predict when to take turn at specific opportunities. And we want to identify these opportunities in an ecologically valid manner. And in order to do that, we developed an experimental paradigm. So here's a speech segment of two people having a conversation.
Oh, now you started. In those days, I started at 9:30 and 9:45 instead of 8:45.
Yeah, we like.
And I want to define a few terms using this segment. So the first term is a turn construction unit, which in conversation, we can think of it as an atom of turn taking. That can be a word, a phrase, a sentence that just makes standalone sense in that particular context. We know that a collection of TCUs by the same speaker, typically within 1,000 milliseconds of each other, is a single turn by that speaker. And then most importantly for my work, we have these transition relevance places, which are when the speakers actually switch who is speaking, right? So these are opportunities where other people can talk in the conversation. And then in my operationalization, I say that TRPs have both a discrete time at which they occur. So that's represented by the vertical lines here. And they also have an offset from the closest TCU. So if the offset is a positive value, that means that person A stopped speaking and then later person B started to speak. And if it's negative, that means that the two people overlapped. There's also two subcategories of TRPs that I want to define. So the first one is TRPs between turns. So this is the scenario where someone's speaking and then they stop speaking and someone else starts to speak. The next person started to speak at a TRP point, which occurred between the two turns. This is really easy to retroactively identify because we can tell when different people started to talk. We also have TRPs within turns. So imagine two TCUs by the same speaker. And there might be a TRP between these two TCUs where some other person could have responded, but they didn't actually respond. And these are difficult to identify retroactively because someone didn't respond. They just felt like they could have responded. We also know that these TRP points where people do respond and also don't respond are very, very important. We're oriented towards these points. So we make a number of turn-taking decisions at these points, and we actually are predicting these points in conversation, which allows us to have this rapid turn taking. So the problem here is that we can annotate TRPs between turns, but we can't annotate TRPs within turns. The reason is that there's individual variability of actually responding at TRPs within turns, and then they're difficult to identify in an ecologically valid manner. And what that means is in a way that actually happens. Yes.
You now use the term I don't know twice, ecological validity.
Yes.
Quickly explain that.
Yes, absolutely. So ecologically valid in this case means that we are able to identify these TRPs in a way that we would have done in naturalistic normal conversation, and that it generalizes to other data sets as well. So it's not like particular for our data set. Yes, thank you. So here's an example of a stimulus in our experiment that we did. The idea was we took a part of our recording that was actually a dialogue, and we took one part of that dialogue. So this is just one person speaking in the dialogue, and it contains multiple opportunities for someone to respond. So here's an example of a single stimulus in our experiment.
There have been times in like
My friends and I checked beforehand, like going to a party to see if there were Ubers around that person's house, because a lot of times they lived in the middle of nowhere. And like there just wasn't, so then we'd have to drive because we knew we wouldn't be able to Uber that late. But like, I don't think that's gonna happen.
So that's a single stimulus. And then what we did is we made a stimulus list, which is a number of such stimuli that are independent of each other. So they're from different conversations. And we combined them into one audio file, and we separated each stimulus with some sort of demarcating noise, like the beep that you just heard. And we then asked participants to respond, to listen to these stimulus lists, and then respond at points where they thought that it would be appropriate to respond. And we had 120 participants and 4 lists. So we had 30 participants per list. And because we know that, these TRP points are kind of there, we can all tell. And there's individual variability in when people actually respond. We expect some sort of distribution around some point for when the TRPs actually occur. Yes.
What do you mean by response?
Yes. So when people say a one-word utterance, so they might be listening to a turn, and then they might say, uh-huh, yeah, so on. One-word responses. Here's an example of what we found.
There have been times when like my friends and I checked beforehand, like going to a party to see if there were Ubers around that person's house, because a lot of times they lived in the middle of nowhere, and like there just wasn't, so we'd have to drive because we knew we wouldn't be able to Uber that late. Yeah. But like, I don't think it's gonna.
So with that, I want to briefly touch on the fact that we did empirically justify our treatment of TRPs as 2 distinct categories. So we know that TRPs between turns and within turns are 2 different things, and they're not the same thing. We did this using TCU level data from the switchboard corpus, which we validated using Gilbot, and we were able to collect the types of TRPs that we had. And we used a number of analyses to show that these are actually distinct categories of TRPs, and we published that work. But for the sake of time, I'm not going to go into too much detail here. So the third thing we wanted to do, now that we've identified TRPs, we have like our 2 different types of TRPs, and we have Galebot, which can generate data at scale, was how can we predict these TRPs in spoken language? And can we use large language models for this purpose? And our approach was to first figure out how well these large language models are actually models of spoken language. And in order to do that, we treated these large language models as participants in a psycholinguistic style study. So I want to make a distinction between 2 types of language first. There's written first language. That's language that we would write down and then maybe someone would speak. And then there's spoken first language, which, we just spontaneously say. And we know from a lot of research that these are 2 different kinds of languages. Like they're fundamentally different in their norms and their content. And one distinguishing characteristic of spoken language, spoken dialogue, is who is speaking. And who is speaking actually changes the meaning of what's being said, and also the plausibility of what's being said. And we wanted to use large language models to see how well they capture this difference. So what do I mean by this? Imagine that there's a speaker who says, "Why did you turn the AC off?" And then the same speaker says, "I'm hot." That makes sense because they're explaining why they asked the question. And then if a different speaker says, "Sam did," that also makes sense because they're responding to the original question. And these are congruent second turns. They are plausible. They're less surprising. They're more predictable. And then we also have the case where if we just switch who said what, so if the same speaker said Sam did, that's weird because now they're answering their own question. And then if a different speaker says I'm hot, that's also weird because now they're providing the justification for the question. So these are incongruent turns. They're implausible. They're more surprising, less predictable. And the only reason we have this is because we switched who was saying what. So Warnke and de Ruyter did an experiment where they used 2 turn sequences to determine second turn surprisal in humans, right? So they measured this effect and they found that the second turn, that is incongruent, is always more surprising than the second turn that's congruent. And regardless of who is speaking in the second turn. So if it's the same speaker or a different speaker. And we wanted to use large language models to generate turn surprisal for all of our stimuli that Warnke and de Ruyter used. And we have a few relationships to keep in mind here in our work. So we know that predictability is a function of both context, so what is being said, and then who is saying it. We define surprisal as a measure of uncertainty in a particular event. It's just how surprised you are, like the natural intuition that you might have, and that's mathematically defined as the sum of the negative log probabilities. And then we know that the more predictable something is, the less surprising it is. And the more surprising something is, our brain kind of starts to go a little haywire if it's surprised. So I want to quickly walk through an example of how we would actually calculate surprisal using a large language model. On the top, you have two terms that are stimuli. That's one stimulus from Warnke and de Ruyter. So speaker one says, why did you turn off the AC? Speaker two says, Sam did. And then the large language model generates the probability of the word given the context and the model parameters. So if we had the context with the speaker labeled, why did you turn off the AC? And then speaker two. And then we wanted to know the probability of Sam given that context, that's some number. And then we change our context to then have Sam in there as well. And we want to predict the probability of did, that's some other number using the large language model. And then the surprisal that we have is just the sum of the negative log probabilities. And yeah, there's a formula that's on the slide as well. In this case, I took some random numbers, sorry. And then that value is 1.7. So in order to actually do this, we use two variants of GPT-2, which is a type of decoder-only transformer model. And we fine-tuned GPT-2 on a corpus of natural interaction that was collected at our lab, the Human Interaction Lab. And this was conversations between 20 to 30-minute conversations between undergrads who were just kind of naturally speaking to each other. So we tried to mimic natural conversation in this case. In our training data, we added start and end labels for different conversations. We also added speaker labels for different turns. And here's an example of like one conversation. We also validated our annotations and our segmentations of turns and TCUs, both manually and using Galebot. And we trained our models on 28 different conversations from this corpus. We also used Turn GPT, which is just a variant of GPT-2. And all it does, in addition to word and positional embeddings in GPT, which define what the words are for the model and the relative order in which the words occurred, we also define this other type of embedding, which is speaker identities. So that tells the model like who is actually saying what. So we tried to explicitly put that information in as well, even though implicitly that's probably also captured by the model using our speaker labels. And then we implemented this from scratch, and the code is open source. And we trained this in the same way as we would regularly train a GPT-2 model. So what did we find? We found that the incongruent stimuli were more surprising than the congruent stimuli for the different speaker condition. So when the second turn speaker was different, our hypothesis was matched. It was the same as our findings in the natural data in humans. But when it was the same speaker in the second turn, we found that incongruent stimuli were less surprising than congruent stimuli. And then this is really unexpected in our case. We interpret this as the model hallucinating speaker switches. So the model actually thinks that speakers are continuing when a different speaker has started to speak. And we conclude that the models do not replicate human surprisal trends using multiple analyses that are in the paper, which is currently under review. And what we take away from this is we shouldn't use large language models as models of spoken language or as participants in a psycholinguistic study to actually study human communication mechanisms. And this is in line with some previous research that actually suggests that these models learn formal competence, which is something like statistical rules, the patterns of words, or the norms in the language, but they're not learning functional linguistic competence, which is how those words could actually be used or how you could use upper level knowledge, such as speech acts, to predict upcoming conversation. So to summarize, what I did in the course of my research was to first develop a tool that automatically annotate paralinguistic features of conversation. We then generated a corpus of natural interaction containing annotations of TRPs in an ecologically valid manner. We justified our treatment of TRPs as two distinct categories. And then we concluded that large language models cannot yet be used to predict TRPs in spoken language reliably. With this work, I have a number of future inquiries that I want to look into. So the first one is that in natural conversation, we also have access to nonverbal behaviors. We also have access to acoustic information that we can use for predicting upcoming TRPs. And there's a lot of debate in the literature about which one of these is more valuable. So we can use transformers as a way to analyze that and see what is actually being used by the model to identify upcoming TRPs. We can also develop a probabilistic notion of TRPs at between silences, like how I showed in that previous example, where there's individual variability in when TRPs are actually going to occur, and we can model that probabilistically. And then the final question is, how do we put all of this in incremental and continuous spoken dialogue systems, which are spoken dialogue systems that are continuously predicting what's going to happen next, instead of waiting for someone to finish what they're saying and then moving on. Finally, I would like to thank all the members in my lab, Julia, Lena, Saul, JP, the High Lab, and then Sage, which gave a grant to Gilbot. And then I also want to thank my family for all their help. And then, yeah, the audience for coming. Thank you.
Question turn.
Grace, could you check the Zoom as well? Yes.
So certainly, like if tomorrow the Google Assistant started saying like, yeah, I don't know why I was speaking, I would be concerned and confused. Do you think that that's something we would get used to pretty quickly though, or is that, you know, like, is that purely because it's not expectation, like, you know, it's not behavior I currently expect, or?
Yeah, that's a really good question. So when we're actually having a conversation with each other, we are very well trained in how we use language and how we coordinate who is speaking. When we're speaking to a robot or spoken dialogue system, we adjust our expectations eventually because we're used to those systems speaking in that way. So I suspect that it would be just a readjustment of expectations that would lead to more efficient communication with the system. Do I have a Zoom question? Okay, so we have a question that says, do you think your findings generalize to different turn timings in different languages? That's a really good question. I actually have a slide for that question. So previous work has found that there is variation in different languages and cultures about the average response time between turns. So for example, we would go to certain, we would hear certain languages and say they're speaking really quickly or they're responding really fast or slowly. That difference does exist, but the underlying mechanism of coordinating turns between different speakers also exists universally in these languages, and that's what we're trying to capture. Good question. Thank you.
Okay. So in the last part of your work, what I see is you're telling that with transformer model, you can test the how surprised the response will be, right? And then you show that the prediction is actually different with our human understanding. But how does that let you conclude that the transformer cannot predict TRP? I don't see the how.
So what we
from that.
Yeah, thank you for the question. What we did was we compared the surprisal trends between the humans and the large language models, and we wanted to show that the surprisal trends are not the same, and that the model would, if we actually used it in a real context, would hallucinate speaker switches in some case, which it does, right? So you can imagine a model predicting an upcoming speaker switch when there's actually a speaker continuation. And the goal of our work was to show that we can't reliably yet use these models to study human interaction or to predict these TRP points, because that would be a prediction of the speaker label that the model isn't capturing correctly based off of the speaker identity.
So you're basically saying that the model cannot even tell that's a different speaker, not only say that they're predicting the TRP.
Yes, yeah, yes.
Thank you.
Sam.
Could this be coming from like, I guess like a terms of people bigger, will this problem go away? Or is this like a fundamental problem with transformers themselves?
So that's also a really good question. There's a paper that recently came out. It's called The Curse of Recursion that claims that increasing the amount of training data for large language models does not improve functional competence for the large language models. What I personally suspect is if that we were able to train these large language models from scratch on actual spoken data with information about who was speaking, then these models would be much better at predicting that. Yeah. Yes. More parameters for the model? Yeah, I think it's the same answer in that case as well. Yes.
I'm curious your reaction to this notion. So it looks like the work you're doing will make computer chat systems more like humans. Is this a good thing or bad? There's another point of view, Ben Schneider used to espouse it, that if a computer should behave like a computer, it shouldn't try to be my friend or try to be a person.
Yeah.
I'm just curious your comments on that.
Yeah, that's a really good
It's not
question.
gospel, it's just
No, that's a really good question. In fact, we know that there's uncanny valley effects with actual robots. If they look too realistic, then we kind of get freaked out. It may be the case that there's some similar uncanny valley effect with spoken dialogue systems. The answer is that we don't really know because such a system doesn't really exist right now. The idea here in our work is to be able to give these language models the ability to use our mechanism for having a conversation so that they might be able to, more efficiently communicate, more efficiently recover from miscommunications if they actually happen. Thank you.
another possible answer is humans are already trained on how to talk to other humans.
Yes.
Why make them train on something else?
Yeah, exactly.
The other thing I was gonna say is, you said you don't know how to do this yet. You can do Wizard of Oz experiments.
We can. Yes.
As a way to see if this would be any good, even if you could build it.
Yes, and that's one of our future works where we want to do our experiment where we detected people saying yeah at the right time with robots as well, maybe in a task-oriented setting, and see what the difference might be in that case. Yeah, that's actually my RA Grace is working on. Yes.
You mentioned briefly parallelism in the context of Galebot, but not much else about computation. I'm wondering if you can walk us through what roughly are the computational costs, both of your experiments and sort of what you imagine down the line in a real-time spoken dialogue system. We're talking your computers, data centers. Give us a sense of what the costs are.
So we have dialogue systems that exist currently that are able to produce responses really, really quickly while they are running on a single computer, right? So that's absolutely possible. Once the models are trained, we have systems that can do that. The problem happens when we want systems to just respond in a naturalistic manner, in which case we need a discourse manager, which actually manages the higher level information of what is happening in the conversation. And we also need an action manager, which is saying, based off of what the person has said and then what the system has already communicated, what is the next course of action for the system? So this computation basically takes a lot of time. And doing this on the order of 200 milliseconds, which is our average response time, is difficult. And sometimes we even respond faster than that. So we might have situations where we start speaking before someone else has ended. And there's evidence for this because we typically start looking at someone before we start speaking with them. So the idea here would be to have a system that is able to kind of do that and predict that within that short time window. Yes. Does that answer your question?
That's a good part of it there from the end. You mentioned parallelism. Parallelism is only going to be mentioned when costs are important. Let me just ask you a simpler question. Where's the biggest computational cost in the work you've done so far?
Yeah, so it definitely in the transcription for the corpora. So we have a corpus, for example, the call home corpus or the switchboard corpus, which are very large, collected in like the 1980s that have a lot of telephone conversations. And if we were to transcribe these conversations, even in a system that wasn't parallel, then it would take 40 minutes for each conversation to be transcribed. If the transcription system were able to do the transcription in the same time as the length of the actual audio. But with Galebot, we're able to parallelize all of those transcriptions at the same time. as well as how those paralinguistic features are identified. So we've done an experiment where we calculated that we could transcribe the call home corpus within an hour and a half, all of it.
And what
Using it.
kind of hardware do you need to make that possible?
Just my normal MacBook. Yeah.
Other questions? Excited to see you again.
I take a little bit of a break now, and I think, Cooper's gonna, are you going into the other, are you going into Route 265? Or not?
Yeah.
You can if you want to, we just want to meet, and ask more questions, 265. Okay. So the next talk, actually, we have a little bit of a break because the next talk is starting.